Right, so we're going to talk about thermodynamics, which is basically heat. The first thing that you should be familiar with at some point, hopefully you saw this in a general science course, energy cannot be created or destroyed. It can be changed from one form to another. So if that's true, these little hand warmers that you can buy, they're pretty cool. Here you can see it's 70 degrees. And then when you get the reaction started by bending this coin, you turn the red gel into a solid. And as you see, when the solid forms, it gets significantly hotter than the 70 degrees Fahrenheit. So if that's true, hopefully, and if we were in class, I could hand these out. So if that's true, then where does the hand warmer get its heat from? And hopefully you realize there's a reaction going on, and that reaction is releasing heat. So what we say is the reaction, the chemicals, are the system, and then the heat gets released to the surroundings, all the area around, and that's how you can warm your hands. Your hands would be the surroundings getting warmer because of that system, the chemicals going through that reaction. So the energy diagram would be that the gel must have more energy than that solid that forms, because in the process of becoming a solid, it's able to release that heat. And it took a little activation energy for that to happen. I had to bend that coin. So what we say is that the overall energy change, the gel was actually 6.56 kilojoules higher than the solid. And in the process of that reaction, it went down 6.56 kilojoules to reach the solid. And we call that the delta H, or the enthalpy of the reaction. So we call these types of, so that's the activation energy. We call these types of reactions exothermic, things that release heat like this. There's always a little activation energy. The overall change will always be negative because the reactants must have more energy than the products in order for them to release heat to the surroundings. So that heat released to the surroundings came from the fact that the reactants had more energy than the products, and in going to the products, they released that heat. Here's what happens next. It's called an endothermic reaction. So I take that solid that formed, put it into boiling water, and I can put the heat right back in there so that you can reuse this hand warmer. So by putting the heat back into the hand warmer system, so now the surroundings are pushing heat into the system, right? And then we got that clear gel again. So in that case, the reactants were low energy. That solid turned into the product, the gel. We had activation energy. It was much larger activation energy now. I had to boil it in water. It wasn't just bending a little coin to get it going. And the overall enthalpy, the delta H, will be positive because the reactants to get to the products had to get heat from something to get up there. So there is heat put into the system from the surroundings. All right. So another thing you need to know is that heat is to cold as light is to darkness. There is no such thing as cold, just the absence of heat. And there is no such thing as darkness, just the absence of light. So think about it. Your refrigerator is cold. The reason it's cold isn't because cold is getting pushed in, it's because heat's getting pushed out. If you feel around the vents at the bottom of your refrigerator, you'll feel hot air coming out. And if you go to a supermarket and you go to the freezer aisle, you'll feel hot air coming out of the freezers into the aisle. And that's because the hot air is coming out of the refrigerator and into the surroundings. So it's coming out of the system and into the surroundings. So I want to show you this heat vet, which I think everyone should do. So the heat vet, you want to hit this little energy symbol so that you can see the energy symbols. And then notice that as I raise the temperature of this iron block, I'm putting energy blocks in there to raise the temperature. So there is no such thing as cold, because watch when I put the temperature down, cold isn't going into the iron, energy's coming out of the iron. So I can put the energy back in, and the temperature goes up. So the energy moving into the iron is what makes the temperature go up. It makes the atoms of iron start vibrating faster so that that temperature can measure the kinetic energy of those atoms moving around. So energy goes in, that's what heat is. Energy comes out, that's what cooling is. But heating is the only thing that really exists. You either pull heat away or you put heat in. Now watch when I put this brick on there, notice the heat goes into the brick, right? The energy is going into the brick, and then the brick and the iron reach the same temperature. That's called thermal equilibrium. All right, so let's explore this a little more. So you should be able to do that on your own. So the definition. So temperature, remember, is average kinetic energy, how much things are moving around, whereas heat is the energy transferred between objects at different temperatures. The symbol for temperature, thank goodness, is a T for temperature. That makes sense. Unfortunately, they gave heat the symbol Q. I don't know why they gave it a Q. It's not very helpful that it's a Q. But we'll talk about some things that you can do instead of that. I will never, ever ask you what's Q the symbol for. It's trivial. So the units of temperature are degrees Celsius or Kelvin, whereas the units of heat are joules or kilojoules. If we're going to measure temperature, we use a thermometer. So we get to use an instrument that measures how much kinetic energy is moving on. Heat, you have to calculate with math. So you don't have something that measures heat, believe it or not. You have to calculate it. The temperature is helpful in calculating the heat, but you have to use some other things to do that. So heat is one direction. It goes from things of higher temperature to lower temperature, right? Those energy blocks in that FET had to go from higher temperature to lower temperature. And that keeps happening until they reach thermal equilibrium, which is when objects are at the same temperature. So the substance that gains the heat has a positive value, right? Because the surroundings are putting heat into the system, and anything that loses heat would have a negative value for the Q because the heat's coming out of it. So the iron block was losing heat to the brick. So the brick had a positive Q and the iron had a negative Q. So there's this term called specific heat. And again, thanks to the abbreviation gods, they made it a capital C with a subscript P. Not the best choice, but that's what they did. And it's the amount of energy required to raise the temperature 1 gram of substance, 1 degree Celsius, or 1 Kelvin. So the units turn out to be the joules, the heat required for 1 gram, 1 degree, so joules per gram degree Celsius. And this will depend on what kind of material is changing temperature, how much you have, and what the change in temperature is. So let's take a look at some. Here are some here. So high specific heat means that these substances require a lot of energy to change a gram 1 degree Celsius. Now you might see plastic, styrofoam, air, right? Some things up here that you're not very worried about as far as putting heat in you, but that's because their density is very low. So water has a higher density. So if you put your hand in boiling water, it hurts a lot. Whereas if you put your hand on plastic that has boiling water in it, it doesn't hurt quite as much. Styrofoam, not at all, because it's not enough mass of styrofoam to push that heat into your hand. Air, same thing. You can put your hand in an oven that's 350 degrees, and it doesn't hurt you because there's not a lot of mass of air to push that heat into your hands. So low specific heat means it doesn't take much energy to move a gram 1 degree Celsius. All right, so here's the equation you need to know for this unit. It's the heat equals the mass times the change in temperature times the specific heat. So the heat will be negative when heat is lost and positive when heat is gained. Don't worry about that too much for this class. The mass is the mass of whatever it is that's heating. Change in temperature, again, I would always take the bigger number and subtract the smaller number. This is important if you are going to worry about whether it's positive or negative, but it's probably easier to think about it at the end, whether it's positive or negative anyway. And less math problems will happen if you just take the bigger number and subtract the smaller number. And the specific heat has to be given, or if you're finding it, then the other 3 things will be given. So here's another way to remember this exact same equation. The specific heat is given, units of specific heat are given as joules divided by grams degrees Celsius. So take the heat, the joules, and divide it by the mass, the grams, and the degrees Celsius, the change in temperature. So this is basically a way to remember this equation using the units of specific heat. Okay, so if I asked you to determine the heat lost or gained for 50 grams of iron going from 20 to 80 degrees Celsius, so I've given you the specific heat, right? So that's going to go there. The grams is given, that's going to go there. The change in temperature, like I said, it's going to be easy to just subtract the higher number, 80, and subtract the smaller number, 20 from that. You can do that in your head at 60 degrees. So we can also look at this equation as just saying, take the joules, it's going to equal the grams times the degree Celsius times the joules over degree Celsius. Notice the grams will cancel, the degree Celsius will cancel, so joules equals joules. Just showing you another way. So you just take those units and find them. Here's grams, that goes there. Here's degrees Celsius, that goes there. Here's joules over grams degrees Celsius, that goes there. So you take the 80 minus 20, you get your 60, right? That goes there. Your grams goes there. Your degrees Celsius, joules per gram degrees Celsius go there. And like I said, the degrees Celsius will cancel and the grams will cancel, so joules equals joules. And so that's how you get how many joules there are in the iron for it to change from 20 to 80 degrees. So let's look at another one. What if I asked you for specific heat? So if I ask you for the specific heat, I have to give you the grams, the joules, and the temperature change. And you're going to put those in order, just like I told you, using, if this is joules over grams degrees Celsius, you're going to take the joules, divide it by the grams times the degrees Celsius. So the joules is the 566, that's going to go on top. 2.67 grams is going to go here. The difference between these two is 55 degrees, and that'll go there. So 55 degrees, 66, 26.7, do all that math out, you get 0.385 joules over grams degrees Celsius. So if you look on your chart, you'll see copper has a specific heat of 0.385 joules over grams degrees Celsius. And we call that an intensive property. It's intensive because no matter how much copper you have, a gram or a ton, it's still going to have the same specific heat. So you can identify things this way using specific heats.